Welcome to session 2 of the Monte Carlo lecture, and I'm going to talk about integration in this session. To start with, consider the classic undergraduate Riemann integral. And what we're going to be concerned about is taking an integral and converting it, transforming it, into an integral with respect to another variable. And what we will do is we need to be able to attend to the a and b, the integrams, and they need to be converted essentially to values associated with the new variable. So in this case, the old variable will be x, the new variable will be u. So we need to take a and b and convert them into their corresponding values of u. We will need to take x and convert it into a value as a function of u. And then we will need to take d of x and convert it into a function essentially of u and d of u, which we'll see how to do in a moment. In order to do this, and in particular, in order to take care of this, but it's essential actually across the board, but for the moment, in order to do this, we need to have a one-to-one function. So this is going to be the case where x and u are related with a one-to-one function. And of particular interest for us, it's going to be, we are going to use u as a variable defined on the unit interval from 0 to 1. That's going to be the main use of this technique for our purposes. So the goal then is to find a way of expressing x in terms of u so that we can rewrite the integral in a way that will be hopefully easier to evaluate. And usually what we do is we use log of x. And the reason for that is that when u is going from 0 to 1, then log of u can be used to reach negative infinity to infinity, 0 to infinity, and in fact negative infinity to 0. Not specifically as a function log of u, but log of u, negative log of u, or breaking it up between the two of those would be able to reach all three of those specific ranges. So for example, if we're going to try to do the evaluation of e to the negative x, an integral from 0 to infinity, we could take x of u, or to say x as a function of u, to be negative log of u. So from that perspective, u, which is going to go from 0 to 1, will span from essentially infinity to 0. When u is 0, negative log of u is infinity. When u is 1, negative log of u is 0. And when u is anywhere between 0 and 1, it will be between 0 and infinity. So we are going to define our u as a function of x. We're going to need both of these. Right? So we have x as a function of u. We will get the inverse function, and we will express u as a function of x. We will also take the x of u expression, and we will look at its derivative with respect to u, which in this case is negative 1 over u. Based on dx du equal to negative 1 over u, we can solve, and we can have dx is equal to negative 1 over u times u. So with these pieces, we can fill this out. We start with, roll up a little bit, we start with our original integral that we're interested in. We will say that 0, if x is 0, e to the negative 0 is going to be our counterpart of u. And when x is infinity, e to negative infinity is its counterpart. Here we have a negative x, so we're going to put in the negative x here, and remember that that is x. We're saying that negative log u is x, so I just plug x in there as a function of u now. And then d of x is, as we wrote up above, is negative 1 over u du. The negative of the negative log u is just log u, and e to the log u is just u, so u times a negative 1 over u is just simply a negative 1. And that integral is the integral from 1 to 0 of negative 1 du. So we took what looked like a fairly complex equation, which, let me erase first here a little bit. We took this fairly complex equation and we turned it into a actually very easy equation. Now it's actually a little bit easier than this. Now you'll notice that the integral from 1 to 0 of negative 1 du looks a little odd. Integrating from 1 to 0, typically we think of integrating in the other direction. So one thing to notice about this type of integral, which is called a Riemann integral, and that is that the equivalence between integrating from a to b of gx is the same as integrating from b to a of negative gx. And I'll explain this a little bit more later, but this is a, at the moment, take it as an identity, this is true. And therefore we could take our 1 to 0 of negative 1 and convert it to 0 to 1 of essentially du, or 1 times du. So our integral is, if you evaluate that integral, you get u evaluated from 0 to 1, and that gives you 1. So we were able to answer this question by evaluating u from 0 to 1. Made it a lot easier. Now let's take another example. In this example, we're going to go from negative infinity to infinity, integrating e to the negative x squared. Well, how can we do this? Well, if we were to take x of u, make x a function log of u, well then x is going to go from negative infinity to 0. And if we take it negative u, we're going to go from 0 to infinity. So we really can't, since that u is a unit interval, we really can't get from negative infinity to infinity. But if we remember in calculus, right here, we can break up the integral. So for any point in the interval from a to c, we can break up the integral from a to c to equal to the integral from a to b, and then add to it the integral from b to c. So we will take our negative infinity to infinity, break it up to a negative infinity to 0, and add it to a 0 to infinity. And now we can do this. We can do this because if you look above, remember we can use the log of u or the negative log of u. We can get from negative infinity to 0, and we can get from 0 to infinity. So how do we do this? Start out with breaking it up. Here is our 0 to 1, e to the negative log u squared, 1 over u. So we're using x equal to log u, plug it all in, and we get that. I'll plug the xu and put it in there. Same thing over here. We use that x equal to negative log u and plug it into the second integral, and we get the expression as expressed there from 1 to 0, e to the negative log u squared times negative 1 over u du. Do a little bit of algebra and work your way through. We can switch this 1 to 0 and switch it around to a 0 to 1. We can note that a negative log u squared is the same thing as just log u squared, so we end up with e to the negative log u, 1 over u du, and the first integral is actually the exact same, so it's twice that. And if you evaluate that integral, you will find the answer is 1.772. Now, in this case, the question of whether it was simpler to evaluate that integral, negative infinity to infinity e to the negative x squared, or evaluate this integral of 2 times the integral 0 to 1 e to the negative log u squared times 1 over u, is a bit, I guess, unclear which one would be easier. But for our purposes, it will actually turn out to be much easier to evaluate this one, because we're not going to necessarily do this by calculus. We're going to do it through Monte Carlo simulation. But for the moment, we're just exploring the idea of transforming the variables. And we don't have to keep it to just one variable. Consider this following integral. So now we have an integral with respect to dx and dz. And the function is x plus z, that quantity squared, divided by x minus z. And I want to integrate that from 0 to z squared with respect to x, and from negative 1 to 1 with respect to z. Here I typed it up in MathCAD, and so I can ask MathCAD to do it directly. MathCAD can directly calculate that, and it says the answer is minus 1.507. But we can rearrange this and use the transformation to variables that are on the unit interval. So instead, I'm going to take my x and my z, and in terms of two variables, u and w, both having unit interval ranges, we will create these functions. So the first one is I'm going to say z is equal to 2u minus 1. Now notice z needs to be able to go from negative 1 to 1. Right? So indeed that's the case. When u is 0, z is negative 1. When u is 1, z is 1. And any point between there will give you a point between negative 1 and 1. So that's successful. Now the second one might seem a little more complicated. And I guess in a way it is. Here you have to remember that we are integrating dx, or x, from 0 to z squared for any given value of z. So we really have x expressed as a function of both z and w, and we want it so that for any fixed z, then as w ranges from 0 to 1, we will go from 0 to z squared. And indeed, this is the case here. So it's z squared times w. So for any fixed z, when w is 0, x is 0. When w is 1, x is z squared. And anywhere in between will be anywhere in between. So we now have our z as a function of u, and we have our x as a function of w. I can rewrite this to have x as a function of uw by noting that z can be written as a function of w and of u as well. And so I can come up with x as a function of u and w. And that's what I really needed. X is a function of the two variables on the unit interval, and z is a function of the two variables on the unit interval, in this case only needing u. So based on these two, we can get our derivatives as we did above, and we can substitute in. Now when you do your substitution in this case, the derivative is actually a matrix of derivatives. And so what we have is the derivative of z with respect to u, and the derivative of, so we have the derivative of z with respect to u, we have the derivative of z with respect to w, and the next row is we have the derivative of x with respect to u, derivative of x with respect to w, times dw du. We plug in the values accordingly above, and now the integral goes from 0 to 1 and 0 to 1. It's no longer a function of a variable because w and u both go from 0 to 1. To do this type of transformation, the matrix, we need the determinant. So this is this parallel line type thing is the determinant. So I plug in the derivatives, and that gives us this. I then tell it to do the determinant, and that gives us 2 times the quantity 2u minus 1 squared. You plug this all into the various parts of the equation as we did above, and we calculate it, and there we go. We get negative 1.507. Here below, I do the same thing, only now I go ahead and instead of writing it as a functional form, which MathCAD can deal with, I just plugged it straight in. So I plugged everything straight in so that you can see that, yep, the equation with everything plugged in will give you negative 1.57, and that is exactly what we had up here, negative 1.57. Only here we're integrating two unit interval variables, w and u, and we're taking each one from 0 to 1, 0 to 1. As opposed to above, we were taking the function as a function of x and z, and we were going from 0 to z squared, negative 1 and 1. And yet, they are in fact the same answer. Is that a simplification? Well, this is a pretty onerous looking equation perhaps, so it is debatable whether or not you could solve which one mathematically easier. You would have to find out, but for our purposes it will be, as I said before, because we will ultimately not be trying to do this in paper and pencil in a closed book exam in calculus class. So we have ways to evaluate it that would allow us to use the transformation to be actually the easier way to do it. Let's go back and review a little bit integration itself. Undergraduate integration starts out with what's called the Riemann integral, and the way that this works is we have some function f of x here represented as kind of a bell curve, and what you're trying to do is get the area underneath the curve. The way we go about it is we chop it up into a bunch of intervals. You can think of that as creating a bunch of points here, and then that creates a bunch of bins. And we create a delta x that is the difference between the two, which is to say it's the width of this bin. Right? So there are my delta x's that I have to find. And then just any point, doesn't matter, any point inside. Just pick a point between x1 and x2, and we'll call that ti, well, t1, I guess. So for each of the intervals, we have a point, interval and a corresponding point. Okay. Now, here you note that this is not, the interval itself is not attached to any absolute value type operator. So it actually has a direction. It can have a sign. It can be a negative or a positive, and that's okay. That will be actually the reason, however, why we had that identity of going from a to b is equal to negative going from b to a, because if you take your integral in one direction, it will give you a negative sign in this respect, and if you take the integral in the other direction, it will be the opposite sign. The integral itself, in the Riemann integral, is simply defined as take each of the intervals, delta xi, multiply it by the function value at that value ti you've arbitrarily picked, and then sum this across all of the intervals. The integral is take the limit as delta goes to 0. Notice that that basically means that I can have this as an arbitrary ti, because essentially it won't matter. And since we're letting delta approach 0, it's really going to be arbitrarily small differences in the function value anyway for any ti within an arbitrarily near 0 value of delta. So that is the definition of our Riemann integral f dx. And again, as indicated here, so this identity, a to b, negative of b to a, it comes down to the idea that this has a sign, and so if I were to integrate this way, and if I were to integrate the other way, I would get the opposite sign. The same magnitude of the integral quantity, but I would get the opposite sign because the signs of these values would be switching. So to keep them the same sign, if you want the integral from this direction to equal, it's going to equal to the negative of the integral from that direction. And so that's essentially our identity that I had above. And that's all well and good. And with MathCAD, we can calculate those integrals very easily. Much of what we are going to do is a little different. We are going to use Monte Carlo integration. To get there, we really need to look at a generalized Lebesgue-Stieltjes measure, or integral, and it's based on measure theory. So this is a measure theoretic based integral, and it is therefore required that we have our measure space. F is our measurable function, and pi, this is kind of capital pi, is the set of all partitions that exist in our sigma algebra. Okay, so we essentially are taking a set of sets. Little pi is a set, and it is a particular kind of set. It is a partition. It's a partition of our outcome space that exists in our sigma algebra. And capital Pi is the set of all those such sets. So now we're going to define a couple of different integrals. One is called the lower integral, and for the moment we will define it as the integral sign with a star below. Now notice here it's often noted as this integral sign fu. There is no du in there, it's just f, I'm sorry, not u, that should be a mu, f mu. This here is the measure. So it is the integral of the function times the measure. And it is defined as follows. You take a particular, this is a little pi, particular, and this is a capital pi. So over the set of partitions, pick out a specific partition, and then go through each of the elements of that partition. You take set EI, you find the element in that set that gives you the smallest function value. You take that smallest function value and you multiply it times the measure of that set. You then go back and you get another element of little pi. You find the function value that's the smallest across the elements in that set of the partition. Multiply it by the measure of that set. And you proceed across all the elements in that particular partition. And so let's say we have partition 1. And when I do this, it gives me a particular number. Okay. Now I go and I pick the second partition that's in this overall set of partitions. I replace this with the next one. Remember that it has a whole set of partitions. I take the next partition, and I do the same thing with that partition. And so that partition 2 will give me some other number. And we keep going until we've exhausted all of the partitions. I'm saying n partitions, but all the partitions, we have a number. Now, we look for what's called the sup or the supremum. We look for the number that is the largest. So out of all of this, we pick the largest of those. And that largest number, that is the integral. All right, so this integral value is the largest number of these summations of function values within sets times the measures across all possible partitions that are in the sigma algebra. Now remember, they're not partitions of the sigma algebra. The sigma algebra are sets that are defined in terms of the outcome space, omega. So they're partitions of omega that are in the sigma algebra. The upper integral, with a star at the top, is nearly the same. The only difference is you, for each element in the set, you look at the largest value of the function. And then you do the summation per usual. But now you go across all possible partitions. Once you've done all the partitions here, you look at the smallest value. So they're just kind of the reverse of each other. And one takes advantage of the smallest value of the function within each set of a partition and finds the largest overall value across the partitions. The other one looks for the largest value of the function within each set of a particular partition, creates the summation, and then looks at the smallest across all of the partitions. If they are equal to each other, then it is simply denoted as the integral fu, or f mu. These are all mu's. Make these look like little Greek letter mu's. Okay. So this is the basic definition of this measure theoretic type of integral. There are some other ones as well, but these are the ones that will be of interest to us. And typically we're working with this because if our integral is considered to be within a continuous space, there's some mathematical regularities that will make this be the case. So we won't concern ourselves too much with the details of differentiating the lower with the upper integral. Now notice that the measure itself is always positive, and therefore that identity with the Riemann integral of a to b equals to negative b to a is not true anymore. Because unlike the dx or the delta x that could go negative or positive, in this case that's not true. The measure is always positive, and we're essentially just simply going through each set. We don't have a defined, that's the point, is we don't have a defined oriented interval. It's just a set of values that we're picking in. So this is definitely not the case anymore. So it's best to denote it in a little different way, to put the set over which mu is, the function in mu is being applied. Right? So just denote it at the bottom rather than go from A to B. That way we don't confuse ourselves with a sense of there being a direction. So the Monte Carlo integration that I just described, which is going to be based on the Lebesgue-Stieltjes integral, or rather the Lebesgue-Stieltjes integral is what we're going to, which I just described, is what we're going to base our Monte Carlo integration on. So this ends session 2, and next we're going to talk about density functions.